Now we come to the exercise 23. So we start a winding number. So what is a winding number and some more properties of a winding number? We come to that. So suppose we are given a closed and oriented curve in the XY plane. We can imagine a curve as the path of motion of some object with the orientations indicating the direction in which direction in which the object moves. Then the winding number of a curve is equal to the total number of counterclockwise turns that the object makes around the horizon. When the counting the total number of turns counterclockwise motion counts as positive, while clockwise motion counts as negative. For example, if the object first circle the horizon 4 times counterclockwise and then they circle the horizon once clockwise, then the total winding number of the curve is twice. For see, observe once again I'm writing when the total number of turns counterclockwise motions counts as positive. Counterclockwise motion count as positive, where the clockwise motions counts as negative. For example, if the object first circle the horizon 4 times the counterclockwise and then they circle the horizon once clockwise, then the total winding number of the curve is 3. In complex analysis, the winding number measures the number of times a path counterclockwise winds around a point where the Cauchy index can approximate how the path winds. We formalize these approximations in the Isbell theorem, a proverb. We provide a tactic to evaluate a winding number through a Cauchy indices. By further combining these approximations with the argument principle, we are able to make use of a remainder sequence to effectively count the number of complex roots of the polynomial within some domains, such as a rectangular box and of plane. See, what is the counting number, the definitions and introductions and the formula of the counting number. See, counting number is given by n times of gamma z. N times of gamma z is equal to 1 by 2 pi I closed path gamma dw by w minus z. See, this is 1 by 2 pi I is closed path gamma dw by w minus z is measure how the path gamma winds around the complex point z. It is an important object in complex analysis and it is evaluations is obvious unanimous means obvious among the analytic group. Ubiquitous among the analytic groups. Secondly, the motivating example in the formalization of a Cauchy residue theorem, we demonstrated an application of this theorem to formula evaluated an improper integral in the theorem say Isbell. So integral of minus infinity to plus infinity dx divided by x square plus 1 is equal to pi. So the idea is to embed this integral into the complex plane and as the illustrated from the figure to construct a line path L from minus R to L, construct a linear path L from minus R to R and semicircular path CR. See, this is the notation say to construct a linear path is LR. Linear path denote LR from minus R to R. Semicircular path we denote CR. Center at 0 with the radius R greater than 1. See, denote this. CR circular path LR R times of e power I pi I for t belongs to closed interval 0 to 1. So linear path LR we denote LR of t is equal to 1 minus t of minus r plus tr for t belongs to closed interval 0 to 1. Therefore, next we lay f of w is equal to 1 divided by w square plus 1. For r tends to infinity, we can derive 1 through the following steps. Say, integral of minus infinity to plus infinity dx divided by x square plus 1 is equal to closed path LR, linear path f is equal to closed path linear path plus circular path f. So this is called a linear path is to linear path plus circular path, call this equation as 3 is called equation as 3. We come to the example. We see this is a linear path from minus r to r. We observed in the graph, if we observe the figure, the linear path moving from minus r to r, we come to the circular path. See the direction. The linear path moving from minus r to r, come to the circular path as CR. So the CR, again in the image of the circular path is CR dash. So this is the image CR dash. We observe the figure A. Come to the figure B. In the circular path, if we take half of the portions above portions, minus r to r, a linear path, you come to the circular path. This is above this. Image D, if you observe the I minus I, so that is a linear derivative, means that is the imaginary, the LR dash, linear path, means is run from minus I to I form. That is called LR dash. See, in the complex point, is 0 comma minus I and 0 comma I. So complex point 0 to I and 0 to minus I, and a closed path LR and CR. The closed path LR plus CR. That is n times of linear path plus circular path, comma I, the residue of f into I, comma I, plus n times of LR plus CR minus I times residue of f minus I. I call this equation 4. This totally we get a pi times. This is called a pi. That is called as phi. The equation 4 and 5 say LR plus CR is formed by the appending CR to end of LR. And the residue of Fi is the residue of F and at I. Residue of F at I. Equation 3 is because the closed path CRF equal to 0 and R tends to infinity. The applications of the residue theorem is within F4. The exploit the fact that I and minus I are only to singularity of F over the complex plane. Since when carrying out a formula for proof of phi, surprisingly the most troublesome part of the proof in evaluating the winding number. So n times of linear part plus circular part times of I equal to 1. So n times of linear path plus circular path, comma I equal to 1. We call the equation 6. The n times of linear part, circular part, comma minus I equal to 0. I call this equation 7. So equation 1, 6 and 7 are straightforward to humans. As it can be seen from figure 1, I already in the previous figure, that LR and CR passes counterclockwise around the point I exactly one times. So and around minus I 0 times. However, the formula deriving this fact was non-trivial. See, these are the basic winding number. What's number of crossing, number of line crossing, number of circular crossing the path. We come to the example. So prove n terms of LR plus CR, comma I is equal to 1 when defined an auxiliary semicircular path CR dash, where CR dash of t is equal to R times of e power pi t plus 1 for t belongs to closed interval 0, 1. As we can see the figure, as see the circular path and image of the circular path CR plus CR dash form a full circular path with I lying inside the circle. I lying inside the circle. We add the n times of circular path plus circular dash path I equal to 1. That is n times of circular path plus image of the circular path comma I equal to 1. I call this equation 8. In addition, we further prove that the circular path CR plus circular path CR plus CR dash, and LR plus CR are homotopic on the space of the complex plane except for the point I. So we accept the point I, that is to say, if we out of that circular, if we take a C in a closed path C, is omitted I times, is omitted I, C minus I, the singly left the I, and hence n times of LR plus CR I equal to n times of CR plus CR dash I. So linear path plus circular path of I equal to circular path, circular dash path equal to I. So that is linear path should be circular path, that is n times of LR plus CR comma I should be equal to n times of circular path plus circular dash path I. So in the same way in the lemma, we come to the lemma, see winding number homotopy path. So it fix Z complex, y1 gamma 1 gamma 2 is a real complex. Assume homotopic path minus Z gamma 1 gamma 2. So winding number gamma 1 Z equal to winding number gamma 2 Z. See where the winding number gamma 1 Z encodes the winding number of gamma 1 around Z varies from gamma n times of gamma 1 Z, and the homotopic path encode the homotopic propositions between the two paths. Putting equation 8 and 9 together yield the n times of linear path, a circular path I equal to 1, which conclude the whole proof. This is the way to prove the winding number. See, if we come to the one more example to prove n times of linear plus circular path linear n times of LR CR plus CR minus I equal to 0. We started by defining the array LR dash starting from minus I and pointing towards the negative infinity of the imaginary axis. Negative infinity of the imaginary axis, that is LR dash of t equal to minus I minus ti for t belongs to close 0 to open interval infinity. T belongs to 0 to infinity, close and open interval. As an illustrated in a figure, say is a subsequent, we saw that LR dash does not intersect with the LR plus CR, and then applied the following lemma to Isabel. The winding number X, we fix Z W complex and Y gamma and real complex. So assume the valid path gamma and Z the path image gamma, and winding number does not belongs to Z, is not intersections of that's real 0 less than A, Z plus A. So that is where winding path winding path gamma assume that gamma piecewise continuously differentiable on a closed interval 0 1. Piecewise continuously differentiable on a closed interval 0 1. The Z does not a path image gamma assert that Z is not a path gamma. So assumptions not a intersection assert that the ray starting at Z belongs to C and the throw W belongs to C, that is Z plus A times of W minus Z. A positive does not intersect with gamma for all A positive, that is A plus Z plus A times of W minus Z does not lies on gamma. So note that this the real part of the bending number, the residue of n times of gamma Z measure the degree of the bending degree of bending. In case of gamma bending around z counterclockwise for exactly one turn, we have n times of gamma z is equal to residue of n times of gamma z equal to 1. Essentially, lemma 2 claim that a path gamma can only wind around z for less than one turn. The residue of n times of gamma z less than 1 if there is a array starting at z and not intersecting with gamma. Joining the lemma 2 with lead to residue of n times of Lr plus Cr of Lr plus R comma minus I less than 1. So residue of n times of linear plus circular path comma minus I less than 1. I call this equation log. So moreover Lr plus Cr is closed path. That is say n times of Lr plus Cr comma minus I belongs to Z. That is it. By combining the equation 11 and 12, we managed to derive n times of Lr plus Cr comma minus I equal to 0. As can be observed in example 1 and 2, our proof of n times of Lr plus Cr comma I equal to 1, n times of Lr plus Cr comma I equal to 1, n times of Lr plus Cr minus I equal to 0, where had occurred the involve the manual construction of the auxiliary paths, and rare similar difficulties have also seen mentioned by John Harrison. When formalizing the prime number theorem, in the next session we will introduce the idea of systematically evaluating bending number. See, we observe the graph. So what is the f of t? What is the s? See, we take an exact y-axis. This is the term if we take an angle z0. See, this is an angle theta. So gamma of t naught, the ray is see the direction of gamma. So bending up. This is an arc theta, gamma t naught. Now, if you come to this in the figure, the second figure, see, say this is the curve f of t. This is the curve. This. So f of t is to be image of gamma of t minus z naught divided by residue of gamma of t minus z naught. So simply say imaginary part of gamma of t minus z naught divided by real part of gamma of t minus z naught. See, this is a transform from z naught to t naught. Transform from the point. This is a pole of z naught. This is a pole of t naught. Here gamma of t naught, here t, that is the way gamma is moving from these directions. So in the figure 2, left a path gamma crosses the line z, real part of z equal to real part of z naught, real part of z equal to real part of z naught at gamma of t naught, such that real part of gamma of t naught greater than the real part of z naught. Write the image of f point travel through a gamma, travel to gamma. Yeah, see, this is the problem. This is the graph of bending number. So theta is an angle. Gamma of t naught is moving from these directions. So gamma. So t naught is down. So f of t. That's the. This is the diagonal C. This is the form of x in the t. F of t. T naught. Yeah.